So the radius, I like capital R more. Radius capital R, right? So we need to know something from calculus 3 here. We need to know that the volume of a sphere is 4/3 pi r cubed, right? So we're allowed to assume that. You can derive that in calculus 3. But the point here is V and R are functions of time, right? Think about that. Both the volume and the radius of this balloon are functions of time. So what does that mean? We can differentiate with respect to time. I'll say we can d dt, okay? So we'll do that. We got dv dt equals d dt derivative with respect to time of 4/3 pi r cubed. Now 4/3 pi is a constant. We can pull that out. And what we get is 4/3 pi times the derivative of r cubed. Well, what's r cubed's derivative? It is 3r squared. Are we differentiating with respect to r? We're not, right? We're differentiating with respect to time. That means there's a chain rule here. We must multiply by dr dt, right? So what we've calculated then is that dv dt is the 3's cancel, so 4 pi r squared times dr dt. Right? And if you look at the problem statement I wrote, you'll find out that we have numbers for the things I wrote on the right-hand side. I told you that the radius was 10 centimeters, right? And I told you that, oh, wait a minute. I'm an idiot. Ooh, I am so sorry. My bad. How fast is, I should have said, good grief. My bad. So sad. Radius. Dummy. Me, not you. So what we're trying to, what is the goal here? Our goal is actually find dr dt. Right? So we're given 3 cubic centimeters per minute. That's the volume per time, the rate of the volume increasing. Right? We're given that's the flow rate in there. And that's equal to 4 pi times 10 centimeters squared times times dr dt, which we don't know. Right? So we solve for dr dt. What do we get? We get 3 centimeters cubed per minute divided by 4 pi times 100 centimeters squared, right? Notice how the units work out here. Centimeters cubed over centimeters squared gives us centimeters. We got centimeters per minute. Let me crunch the numbers here right quick. So 3 divided by 400 divided by pi. Well, it's kind of a small number. 2.38 times 10 to the minus 3 centimeters per minute. Wow. I don't think you'd be able to see that. Did I crunch a number wrong? Or it's just that 3 cubic centimeters per minute is just a sad, sad amount. what's the volume when R is 10 centimeters cubed? 4 times pi times 10 cubed divided by 3. So like the volume, the net volume, oh yeah. So the net volume, to give you a sense of why this is so small, the net volume when the radius is 10 would be like 4,200 cubic centimeters. There's like 4,200 cubic centimeters. Think about it, if you're only adding 3 cubic centimeters per minute, it makes sense that the radius is increasing very, very slowly. It's just because the balloon's pretty big relative to the flow rate. But anyway, this is an example of related rates. Let me show you another example. I won't show you a hard example because we don't have enough time for hard examples. You're going to get 2 easy examples today. Yeah.
Yeah, I have to go like, how long is this example take, this one? Because the lesson ends at 45, right?
Yes.
Yeah, that's in 2 minutes.
That's right, 2 minutes. This one will be 2 minutes. So example 2. A car on track with equation x squared plus 3y cubed equals to 1. If dy dt equals to 10 meters per second, when x equals to 1 and y equals to 0, find dx dt. So what we do is differentiate with respect to time, the given relation. That gives us 2x dx dt plus 9y squared dy dt equal to 0. So we could solve for dy dt and get minus 2x dx dt divided by 9y squared. Right? But we're given x is equal to 1, dx dt is equal to 10, and we have 9 and 0. Have a nice day. This example I've chosen poorly. So yeah, you can't just make, it's possible to make up examples that don't make sense. This is one.
Yeah.
Sorry guys.